Alright, so we're on number 13, and here we're going to be asked to find a second derivative. So, to start off, we'll find the first derivative, power rule for the first term, 3x squared. The second term, we're going to bring down that negative 3, and then take the derivative of the cosine of 2x. Remember, derivative of the outside, negative sign, leave the inside alone, multiply by the derivative of the inside. And then the last term, ln of x, is just a rule. That would be 1 over x. So I'm going to clean up the first derivative. We get 3x squared plus 6 sine of 2x plus x to the negative 1. Now I'm going to take the second derivative. We would get 6x plus, bring the 6 down, take the derivative of sine of 2x, so that would be derivative of the outside as cosine, leave the inside the same, multiply by the derivative of the inside, and then plus the last term, bring down the power, multiply by x to the negative 2 power, and then I'm going to rewrite this just so you can see the other ways it could be written. So 12 cosine of 2x, and then the last term I would probably rewrite as negative 1 over x squared. Letter B, I'm going to rewrite the function as 4x minus 3 to the 1/2 power, so that I know now it's definitely a chain rule. The chain rule would be derivative of the outside would be that power. Leave the inside exactly the same as it was. Multiply by the derivative of the inside function. So now I'm going to clean this up and get 2 times 4x minus 3 to the negative 1/2 power. Now we're going to take another derivative, the second derivative. So I'm going to multiply the 2 by negative 1/2, which gives me just the negative. And then subtracting 1 gives me negative 3/2 power. I'm going to leave the inside exactly the same as it was, and then multiply by the derivative of the inside, which is 4. So my final answer, the negative stays in the numerator, the 4 stays in the numerator, and then the denominator would be 4x minus 3 to the 3/2 power. If you wanted to write it with a radical symbol, you would have the square root of 4x minus 3 cubed. Letter C. So in this case, I'm going to use implicit differentiation because the y is not solved for, and this is not just in terms of x, but remember the question was dy dx. We're taking its second derivative. So to start off, my first term would be 2x. My second term would be 2y dy dx. Remember, we're taking the derivative with respect to x. So any term that has a variable that's not x, I'm going to have a differential. On the other side of the equals, the derivative of a constant is 0. I'm going to solve for the dy dx. I'm going to subtract 2x and then divide by 2y. So you end up with negative 2x divided by the 2y. So I get negative x over y. Now to do my second derivative, I'm going to have to do a quotient rule. Derivative of, low, d of high minus high, d of low, all over low squared. To simplify this, I am going to just rewrite. So I get negative y plus x, but the dy dx is the same as this that we got a second ago, so I'm going to substitute that in now. All over y squared. My next step would be that in the numerator, I now have negative x over y, and then the whole thing over y squared. I'm going to get a common denominator in the numerator. I'm going to multiply this term by y over y, so I get negative y squared. Oopsie, I forgot my squared over my x, minus x squared over y, and instead of dividing by y squared, I'm going to multiply by 1 over y squared. So we end up with negative y squared minus x squared all over y cubed. But if you look at the very beginning, there's actually some extra information that I'm going to substitute in. I'm going to do that by first, and I'm going to come back up to the top. I'm going to factor out the negative in the numerator. What that ends up giving me is y squared plus x squared all over y cubed. But at the very beginning, remember we saw that x squared plus y squared is the same as 25. So I have my negative, but x squared plus y squared is 25, and then divided by y cubed still. So that is actually the answer to the second derivative for letter C. Number 14. The radius of a sphere is increasing at a rate of, so I see dr dt is 2 feet per minute. How fast is the volume changing when the radius is 3 feet? So these are all the information that was given to us, so I put them in their appropriate place. We're talking about a sphere, so in terms of constants, there are none. And so the only thing I'm missing is the formula which they gave. The volume is 4/3 pi r cubed. If I want to find the question, which is dv dt, I'm going to take the derivative with respect to t, so this is a related rates problem. I get 4 pi r squared times dr dt, because the radius is with respect to t. I end up with 4 pi, the radius is 3, the dr dt was increasing at a rate of 2. So increasing means that my rate is going to be positive. So I get 9 times 8, so 72 pi. And if we're talking about volume, the units would be feet cubed per minute. Number 15, what dimensions would maximize the area? So I'm going to maximize an area of a rectangle. So let's come over here. Let's look at this rectangle. I have base times height, but I do know that the perimeter is 24 feet. Well, the perimeter would be 2 bases plus 2 heights, so I get that 12 is equal to base plus height. I get that base is equal to 12 minus h. It's not an equation I can solve, but if you look over to where we started, I need that because I'm doing an optimization problem and there's 2 variables. So now I get that the area is equal to 12 minus h times h. The area is equal to 12h minus h squared. Now that I have one variable, I can take its derivative. The derivative would be 12 minus 2h. I'm going to set the derivative equal to 0. In this case, the derivative cannot equal undefined. We get that 12 is equal to 2h, so h is equal to 6. If I'm talking about heights, I do know that really the smallest height I could have is 0. The highest I could have is 24, but we can't be those values, so there's no endpoints in this function. I know that the largest we could get is 24 because of the fact that they would have to, oh, not 24, sorry. 12 is actually the maximum that we could be, but we could not actually use 12. Alright, so 6, derivative is 0 at h equal to 6. I am doing a line that slopes down. 12 minus 2h is a line that slopes downward, like that. So my sign chart would be plus minus, or you would pick a number in here, maybe 3. You pick a number in here, maybe 10. Substitute it in and get your signs. So I do know, I have verified that this is my maximum, and then I'm going to go back up and see what the question asked. It said what dimensions. So the dimensions would be a height of 6, and then the base is equal to 12 minus height, so we get 6 for the base, and this is in feet. So there's my answer for number 15. Alright, number 16, we're going to graph the function, use the function to estimate the values, and then find the values of C. Alright, so for this type of problem, you honestly wouldn't be asked to graph that without a calculator. So I just brought up a graph using a calculator. from -1 to 2. Use the graph to estimate the values of C guaranteed by the mean value theorem on the interval. So if I'm guaranteeing the mean value theorem, it means that the given at x equal to -1 and at x equal to 2, if I connect the 2 points with a line, hopefully somewhat of a straight line. Let's try that one more time. Then mean value theorem says as long as the function was closed, continuous, and differentiable on the open interval of -1 to 2, which because it's polynomial it definitely is, then I can find at least one place between the two endpoints where the tangent line would be parallel to the secant line. So the secant line is that black line. My tangents look like that would be about where, and maybe somewhere around here. So I don't know exactly where they are, but I can estimate that those would be my approximate C values, and yes, there are 2 of them. And then in letter C, it asks me to actually find the value of C. So to start off, to find the value of C, really what you're doing is you're taking the derivative and setting it equal to the average rate of change. So on the left side, you're actually going to take a derivative. On the right side, you're going to do the slope. Instead of doing it all at one time, I'm going to come over to the right here, and I'm going to find the average rate of change by doing f of 2 minus f of -1 all over 2 minus 1. The average rate of change would then be f of 2 is 10, f of -1 is -8, divided by 1, so we get 18. Or sorry, divided by 3, which gives us, sorry about that, 6. The slope is 6. Therefore, the average rate of change value goes on this side, 6. On the left side, I'm going to find the derivative, 9x squared minus 10x plus 2. To solve the quadratic equation, we're going to write 9x squared minus 10x minus 4 equals 0. In this case, 36. Let's see if this is factorable. 36. And since this one doesn't look like it's factorable, it may be, but I'm not going to spend that much time to try to figure out if it is or isn't. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So we get x is equal to negative 10 plus or minus, let me change my color, square root of b squared, which would be 100, minus 4 times 9 times -4 all over 18. And so we get 10 plus or minus the square root of, so 244 all over 18. And 244 is not a perfect root, therefore we could simplify it by simplifying the root, but at this point that would actually be an accurate value for C. One of them would be plus, one of them would be the negative value. If you have a calculator, you would find the approximate value, which we would do by using this guy, 10 plus the square root of 244, see, enter, divided by 18. So one of the values is about 1.423, 3 decimal places, and then the other value would be 10 minus the square root of 244, divide by 18, negative 0.312, which seems as though it's close, seems pretty close to where I put my orange C value. So if you see here, that does look like negative 0.3. This does look like about 1.4. Not exactly 1.5, but pretty close. All right, number 17. Given the graph of f prime of the derivative on that closed interval, let's see what we get. On the intervals, when is the function decreasing, increasing, critical points? It looks like they're going to ask us a lot of questions about the first and second derivative. So the first thing I'm going to do is create a sign chart, and I'm going to do the sign charts above. So let's do, given that this is f prime, I'm going to do f prime sign chart here. That would be the y values. And the y values would be zeros here, here, and here. So that's negative 3, 1, and 3. The y values here were negative, now they're positive, now they're negative, now they're positive. I'm going to do my second derivative sign chart, which is where I would start looking at slopes. So where my slopes would be 0 would be at horizontal tangents here and here. I'm assuming they're probably right at those integer values, negative 1, and at 2, 0, 0. My slopes are positive because the line is going up, negative because the line's coming down, positive because the line is going up. So now I'm going to answer the questions. So letter A, I'm increasing when my first derivative is positive, so from negative 3 to 1, union with 3 to 4 endpoint, because f prime is positive. I'm decreasing from negative, endpoint, negative 4 until 3, negative 3 I mean, union with 1 to 3, because f prime is negative. Where does f have critical value? So the definition of a critical value is when f prime is equal to 0 or undefined. We see that that happens when x is equal to negative 3, 1, and positive 3. Letter C. Letter C asks us, where does f have a relative maximum or minimum? So maximum would happen when we go from plus to minus. Minus to plus would be a minimum, minus to plus is a minimum. And then if you still have trouble with that, you could always draw your functions. So you can kind of see the max and mins. Now, I just noticed a major mistake that I have is that I didn't end my functions. So, in doing that, I would have missed that this is also a maximum, and this endpoint here is also a maximum. So I actually have maximums at x equal to negative 4 and 0, and then was 4. I have minimums at x equal to negative 3 and 3. So it does ask me to justify. So justifying is going to be a little bit of a pain. So for interior points, at, in this case, f prime of A is equal to 0, and f prime changes minus to plus. For this one, f prime of 0 equals 0, and f prime changes plus to minus. This is a left endpoint, and f prime negative after. And then I'll do the last one in a different color here. This is a right endpoint, and f prime positive before. Alright, so that is a little bit messy, but gives you all the answers there. Letter D says, where do we have points of inflection? If you remember for letter D, I'll come over here. Points of inflection occur when the second derivative is equal to 0 or undefined, and f double prime changes sign. And we have that happening at x equal to negative 1 and 2. Letter D, letter E, when are we concave up? Concave down. So concave up happens when the second derivative is positive, and this occurs when we go from negative 4 until negative 1, and then again from 2 until 4. And then we're concave down in red when the second derivative is negative. Therefore, we have that occurring from negative 1 until 2. And that should be a rounded bracket, I'm sorry. All right. And that's 17. Number 18. So in this case, we have velocity here. Let's see what it asks us. When are we changing direction? So that would be changing direction happens whenever velocity is equal to 0 or maybe undefined, and v of t changes sign. So I'm going to create a sign chart. And because this is velocity, I'm going to use the y values. So here, y value is 0. Here, the y value is 0. And then here, at 0, the y value is 0. My y values are positive, and then my y values are negative. So we change direction at time equal to 7 and 11. C. Letter B. When is the speed the greatest? So graphically, if you're doing speed, you're going to look at the absolute value graph. So the absolute value graph would mean that this piece here in red would reflect across the y-axis, and I would get this orange graph would be considered the speed. So the maximum speed, letter B, occurs at t equal to, I think these numbers are a little off. Sorry about that. No idea why. So at t equal to 10. Again, because we have the graph, I get to use the absolute value graph to do so. What is the acceleration at 6? So the acceleration at 6 would be the slope of the line segment at 6. So I'm going to clear off my graph here, and I'm going to count out 1, 2, 3, 4, 5, 6. Here we go. So what you want to do is you want to make sure that if you are counting slope, it is completely accurate. How would I know if it's accurate? I would use this point here and then this point here. In this case, my slope along anywhere between those two black endpoints would be the same. So I would go down 1, 2, 3, 4, 5, 6, 7, and then go to the right 1, 2, 3, 4, 5, I believe. So the slope is -7/5. Now I'm going to double check that because I want to make sure that I did it correctly for you. So let's go. This was at a height of 3. This is down at -4. Therefore, yes, I'm dropping down 7, and then I'm going from 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep. So the acceleration would be -7/5. I know it's negative because the slope is going down, and then I went down 7 spaces, to the right 5 spaces. If you don't trust that, then you could use 2 points. The points would be 1, 2, 3, 4, 5. So this point is 5, 3, 6, 7, 8, 9, 10, and this 10, -4. I'm really sorry that the values were all shifted. I'm not exactly sure how that happened, but you could always count to make sure that the numbers align with the actual values. So I think that was number 18, so this video should be over. And so